Today we have Ryan Webster who's going to be telling us about extracting training images from diffusion models, and Ryan is just in the process of moving to India.
So welcome everyone. Thank you for joining in. I want to first thank Thomas for inviting me. It's really a pleasure to be here. Today we're going to talk about extracting training images from diffusion models. This was work that I did at the end of my PhD thesis while I was at the Great Laboratory in Normandy, sort of at the start of this year. So I want to start out with just a little bit of context. When I started my thesis, generative AI was really more of an academic subject, and I got to watch it grow into sort of a ubiquitous tool, that even my friends and family use. For image generation, diffusion models are sort of wildly successful because they can generate images from text. So at the right here, I have a picture of my friend's dog, Strider. And if you just plug in, Strider with a cape, you get this sort of amazing generated image on the right here. In order to achieve sort of this level of generality to generate from text, it's necessary to train on billions of images. And the only way to get a billion images is to sort of indiscriminately scrape the internet for everything you can get. And the problem is a lot of these images are owned by other people or copyrighted. So this kind of brings up this hot issue right now of copyright in generative models. And in particular, people actually like to generate content by an artist. So here I've generated some Van Gogh, but you can generate from a living artist's name. And the model has tokenized his name, it's seen his style, it can reproduce his work. So this is sort of an undefined, in terms of the law, subject right now in terms of how do we treat ownership or copyright for these generated images. There's a really nice talk by Pete Henderson in this series, if you guys want to check that out. For diffusion models, it sort of gets even worse. There's many studies showing that diffusion models can sort of explicitly copy data. So they can copy an entire patch and shift it around, or copy a background, or what we'll cover in this talk is copying an entire image. So the objective of this talk will be to find captions which generate copies of training images like this one here. So I plug in this caption, and then I get this pixel for pixel copy of a training image. And so you can see here, this clearly does not happen by accident. This text doesn't contain enough information to reconstruct a sample. So you can sort of conclude this was used for training. And we're going to try to do this. We're going to look through a huge set of captions and try to do this efficiently. So we'll start just by looking at the whole pipeline of the attack, which starts with deduplicating Leon 2 billion, which is a public data set used for training. We'll look at the attacks introduced in the original work of Carlini et al. And our attack. Then we'll examine some results, and we'll look at possible factors that lead to copying. So I'll start with some related work, and kind of the closest work to an extraction attack is a membership inference attack, where we actually try to discern which samples were used for training, given model outputs. So on the right here, I show some medical images that are generated in these left two columns. And then on the right, two real images that you can sometimes very accurately discern these were actually used for training. And so this might be kind of related to what I talked about in the start of the talk is, if you want to prove, let's say you're suspicious your work was used to train a generative model, you want to actually prove that it's used for training, you could use membership inference attack, for instance. Then there's the subject of extraction attacks, which actually aim to reconstruct training samples given model generations. And so the really famous example here is you can do this with language models. And this is problematic because, for instance, if you want to use ChatGPT for medicine, let's say, you definitely can't be spitting out people's medical information. And then finally, there's when we talk about attacks, we always talk about defenses too. So there's the subject of differential privacy, which is a framework that can prevent a model to contain any information about its training samples. So if you do something that's differentially private, you sort of nullify the ability to do attacks. The problem right now is that you take a big hit in model quality. So I've shown here, at this bottom row, is sort of the state of the art for generation with, differentially private trained models. So it's very promising. It's not quite there. So let's take a second just to talk about diffusion models here. So any image generation model, what it's trying to do is sample from a high dimensional probability distribution. And all image generation models kind of work the same. They start by sampling something simple, sampling some noise, and then transforming that into a complex distribution. Now, for diffusion models, there's the opposite process, which is very easy, transforming a complex distribution into noise. And to do that, you just add a little bit of noise over time until it becomes pure noise. Now, to train a diffusion model, it's very simple as well. You just denoise a little bit and then train on a reconstruction loss. Okay, so training is usually really stable compared to some of the predecessors of diffusion models. However, it's more expensive because you have to do these T time steps. And every single step is the evaluation of a deep network, and these are typically very large. So it's more expensive for the quality. So we'll look at the pipeline of the attack now. Kind of the general flavor of extraction attacks is to generate a bunch of stuff. So here I have Layout 2 billion, it's images and captions. So we're going to take those captions, generate a bunch of stuff, use some properties of those generations to sort with our attack function. And then we're just going to check, are these actually copies or not? And the problem is, with billions of images, it's such a huge scale that this is essentially intractable. You can't generate everything. So what previous work has done is use the hypothesis that if we only look at highly duplicated images, and one of the properties of these big scale data sets is that they have a high level of duplication. If we only look at these, then we're going to have a better chance of finding copies. So now we're going to generate only from images which are highly duplicated. We're going to take those captions, generate, let's say, k times. Then we'll run our attack on this and check the ground truth. And in our approach, we'll do this step 3 maybe multiple times. We'll do maybe one sort of inexpensive attack and then iterate with another attack that's more expensive. So let's take a couple notes just on deduplication first. If you want to use a standard approach for deduplication, it typically requires computing a descriptor from the image domain. And for 1 billion points, this is extremely expensive. So luckily, we have the clip features already for Land 2 billion. They were computed during dataset construction. And Carlini et al. Actually deduplicates with these features. Okay, and we didn't have the resources to do this because even this is extremely expensive. The features take up several terabytes of disk. So we chose to use an approximate nearest neighbor search, okay, which makes querying very, very efficient. So what we're going to do is take an image feature, we're going to query its nearest neighbor, and then if it's close enough, we're going to thresh that, say that's a duplicate. Problem is, this object, it really does 2 things. It first quantizes all the features and compresses them, and then it does this approximate search. But this quantization returns an approximate distance where you need to do something kind of special, and I'll show that here. So on the left here, I show if you just take the clip feature y, find its nearest neighbor, and then take a distance, and you get this big spike at 0, and this is just showing that there's a lot of duplicates here. So that's these 2 at the top. They're basically exactly the same image. You can peer at them, they look the same. And then you have this long tail of just sort of semantically similar stuff. And the problem is when you do this quantized approximate search, you get this distance that kind of muddles everything. And the reason for this is kind of technical. So I have a slide at the end if you guys want to know more about this. But the key thing is you want to normalize this approximate distance, and then you get these duplicates back.
Sorry, question on this plot? Yeah. I'm a little bit confused. Okay, so what you're showing here is 3 different distance measures.
Yeah.
In each of these plots. and the arrows of the sandals are showing where the sandals, like which bin the sandals fall into.
Yeah, exactly.
And then on the bottom is the motorcycle, which are two different versions of the motorcycle showing that they fall into different ones for the left bin. Where do they fall for the other two histograms?
So like for this sample here, they would probably fall, later in the histogram.
Okay.
They might, but they could for sure fall into actually the exact same bin for this middle plot. And that's the tricky part. What it comes down to is it basically depends on this approximate search. It does k-means first, and it depends on which centroid it gets mapped to, and that will kind of control the quantization error. So this could actually fall into one of these middle bins here.
Okay, and the argument you're trying to make here is that this right thing is better because it's more efficient?
The argument is that if you want to use like basically the most successful ANN for deduplication, you just have to use this trick to normalize the distance that you get. You can't just thrush it straight away.
Got it. Okay, and the reason why you can't do the left things is because computationally it's slow.
Exactly. Yeah. So this would take,
Okay.
You'd have to do a big distributed thing to do this over here.
Okay. So I see. So you're saying the left thing is the thing that you could do, but it is very slow. It's very expensive. The middle thing is like the naive approach that like wouldn't it be nice if, but like look, the results are terrible. There's no big giant spike on the left. You do the right thing, and now all of a sudden you get the same distribution as the left, but it's much faster.
Yeah, exactly. And like this thing on the right here, it'll actually just get terrible performance, right? Like if you just actually
won't work for.
Yeah. Yep.
Okay. Yeah. Thanks. Okay.
I'll touch on the performance here. So to actually evaluate performance, we do the full deduplication. So we go to every single one of these billions of features, we find their nearest neighbors and thrush it using this normalized distance. And then for stuff that we mark positively as a duplicate, we actually download those images. So another detail here is that Layout 2 billion is a web data set, so it's just URLs. You have to actually download the images. So we download 100,000 pairs, okay, and then we compute their p hash or their perceptual hash, which is sort of like a standard deduplication metric, and then we see like how often we agree. And so what we found was that 700 million images on this huge data set are duplicates. So I was very surprised by this number. I think some people kind of in the community knew of this level of duplication. But it's just surprising, knowing that this kind of causes problems for generative models, that there's so many duplicates here. And what we found is, 84% of what we mark as a duplicate is a p-hash duplicate too. And those would be like these first two columns where, the left image is the query, here's the first nearest neighbor, and you can't tell it apart at all. It'll be, a lot of times it's actually just the same file. And then I show some false positives here where we mark it as a duplicate, but p-hash says it's not with respect to this query. So here this is actually not a duplicate. So our original goal is to get this candidate set for our attack. So let's sort of refocus to that. So let's take a look back at our ground truth again. And what we're going to do here is we're going to differentiate two modes of copying. One is this exact copy. It's a mean squared error, exactly the same. And then the next one is this template copy, where the copy has a mask associated to it, and then it's a copy on that mask. Okay, but there's no shifting here, right? It's just the two images pixel for pixel. So that's sort of our intuitive definition. I'll include some equations here just for completeness. We're going to summarize a generation as G C of J. And that's generating with caption C with seed J. Now, this doesn't mean we have to control the seed. It's just for the sake of the equations, because actually sometimes I have to generate multiple times before I see the copy. And what I'm saying is just if any of these images, any of these seeds are copied, it's an exact copy, and I'm going to label that as a true positive. Okay, and then basically the same thing here with templates, except you also have to retrieve the image. It won't be the corresponding dataset image, and I'll touch on that in just a second here. So let's take a look at this. So if we take this caption here and synthesize, let's say with 5 seeds, for most samples, you get this variation And that's kind of what you expect a generative model to do. You expect new images to be produced. And for copied samples, you get this repetitive behavior. We just need to find one of them, which is the same as the dataset image, to label this as a copy or a not copy. Here we found nothing that's the same, so it's not a copy. Here we found one image, at least, that's the same. Now, templates are a little bit trickier because you get this variation. Well, there's two things, really. There's, when I generate from this caption, I get something that sometimes looks different than the corresponding dataset image. So for this caption, this is an image of a carpet, and then I get these images here. Now, if you generate enough stuff, you do start seeing the same image pop up. So this one here on the left, and then you see it again, you generate 1,000 times, you see it several hundred times. To really see that these are copies, you have to retrieve them. So we'll use the same KNN index that we built before for deduplication. We'll use it for retrieval. We're going to retrieve these guys. Then it's very clear that it's copied. And then you can construct a mask, for instance, take the difference between these two, thresh it, and then that's how we get the ground truth for these copies. Now, I'll just say that for this, for these methods, this was somewhat manual. I would look at the generations and mark stuff to be retrieved, and then this process is automated. So now let's look at the attack functions. The Carlini attack function is relatively simple. And what we're going to do is just look at how many times an image is repeated. So here it's repeated, there's no repeats, 0. And here it's repeated 5 times, so that's 5. Here it's repeated 3 times. So we're going to want to sort by the most repetitive generations, and then we're going to mark those as being copied. Then I've sort of grayed out the dataset images here just to kind of indicate that the attacker does not have access to these samples. He only sees this on the right. Okay. So let's start to kind of fill out this table of the different attacks here. We're going to be looking for the size of the largest duplicate set. We're going to get a set of duplicates within generations, and then look for the largest set. Now, the actual attack function in Carlini is a tiny bit different. It's using graph clicks, but I think this should be the same, or it should be very similar. But this is my implementation. They generated 500 times per caption, doing a full generation. So I say t equals 30, it's sort of good enough to generate something good. So that corresponds to 15,000 generations per caption. Okay. Now our white box attack, what it does is exploit the fact that copied samples pop up right away when you generate with different time steps. So here you can see the diffusion model will add more and more quality and become more realistic as it uses more time steps. But for this caption, Sylvester just pops up right away. And so our white box attack just takes the difference between this initial noise and this generated image with only one time step. We just take the norm here. So we have a different assumption here, is that we need to have access to this noise, which is somewhat unrealistic. I mean, most systems won't allow you to control this noise. And we also need to control how many time steps, and this is more realistic. For instance, for Midjourney, you do have access, you can control the time steps. But what's cool is this takes only one function evaluation per caption. So it's super efficient. And the other thing to note here is that when you generate with just one time step, if you're familiar with the library, and the other detail is that we disable classifier-free guidance, you end up just plugging in the noise into the diffusion model. So there's nothing fancy that happens here. And we subtract this initial noise from this evaluation. And this can be shown to actually be proportional to the score function, which is the derivative of the probability distribution we're trying to model. And so our white box attack somehow captures some irregularity of this score function that we've modeled. Normally we're using this gradient of the score function to kind of push us towards high probability, whereas here we just get mapped directly to the solution. Our black box attack no longer can use that. So what we're going to do is just nix this assumption here. We no longer have access to this XT, and we're going to call this black box. And so we have to use any property we want to discern these two cases. So stuff that's blurry and uncertain versus something that has very clear edges. So I thought of sort of the simplest thing I could use, which is computing binary edges and then averaging over some seeds. And then using the norm of this image, this final image, to have our attack. So it's a little bit more expensive. It takes 4 evaluations per caption rather than just one with our white box attack. And then I'm going to show one more attack here, which is basically just composing the black box attack with the attack in Carlini. So we're going to run our black box attack. We get something that's less precise, and then we get a set of captions, and then we run Carlini on that. So that's what we call hybrid here, and I'm just denoting this, fancy script as this attack spits out a set, and then we run Carlini on that. Now, just for a little bit of to highlight a contribution, if you run the original Carlini attack with the 175,000 captions that they did in the original paper, it takes something like, with the Hugging Face implementation, 5 GPU years to run, and you can run our white box attack in just several days. So this allows for, studying a problem, studying extraction attacks with like very few computational resources. So let's look at our experimental setup. We take the 20 million most.
Sorry, 1 second.
Yeah.
That just in case you're curious, I think that 5 GPUs might actually be even an underestimate. Milad, do you remember? Yeah. Oh wait, Milad was here. I saw he joined. I don't know if he's still on.
He was.
Okay. If you want to make your numbers look even better, I believe that 5 GPU years is an underestimate by a reasonable amount. We had like several hundred GPUs running for like several weeks.
Okay, well, I got the okay from you, so I'll update the paper with you.
No, let me I'll talk to Milad and figure out what the actual number basically is, and then you can like make your numbers look a little better.
Yeah, I mean, I think you guys use 50 time steps. I'm using probably a more efficient sampler, so I said I could use 30 time steps here.
I see.
But what I would say in return is you can actually run, I'm pretty sure you can run your attack or the Carlini attack with much less than 500.
Yeah, you're right. We could have.
So.
But like I guess like there's what we could have done and what we actually did, and like like all of the things that we didn't do. Like I think it's fine to say that like we could have done those things, but like we actually didn't, and so like you can compare to what we actually did as opposed to like what we. But anyway, regardless, it's at least as good as we were saying, and maybe even better.
Yeah, sure. Yeah, this is just rough estimate here. Okay, so we take the top 20 million captions in terms of duplication rates. So the original paper looked at 175,000, and that's how I computed the 5 years number. We actually can look at a lot more now because it's so efficient. We can just go ahead and look at 20 million instead of 175,000. And we gather the exact copies, just totally automated. So we download everything from the top, let's say several thousand, given by our white box attack, and then just verify with MSC there. What we call ours white box is we're just running this white box attack on SDV1. Ours black box is we take to kind of simulate. Now our black box attack is a tiny bit more expensive, so we're just simulating some set of captions. We take 30K captions selected by our white box attack, and then run our black box attack on that. Now for SDV1, it's not technically black box, but for SDV2, it would be. And then for our hybrid attack, we just choose 500 samples and then run Carlini on that. And then Carlini, our implementation is, we just simulate, we take 2K non-copied samples, and then we insert exact copies. So we get this plot here. So what you really care about with extraction attacks is the samples you're most confident on We want to be very precise on those. And so you can see the original Carlini attack in red. So I just took the numbers from the paper and plopped it here. It's very, very precise. So we're looking at how many copies do we find and the most confident samples first and how precise we are. So theirs is almost perfect in this red curve here. Our implementation is matching it pretty well in blue. And our white box attack is also performing well and maybe missing something like 15 copies. Our black box attack it looks a lot less precise, but again, you have to consider, these are 100 copies within, 30,000. And then our black box attack, our hybrid attack is a lot more precise. And some of this weirdness here is actually just coming from labeling noise. Like I checked a few days ago, this point here is actually a copy, and so it gives this noise. But so just to say it's not perfect here, but the hybrid attack really improves the the accuracy or the precision, sorry. Okay. Now for templates, both Carlini and our white box attack are a little bit less precise. So we have our white box in green and Carlini in blue. And the reason for this, at least for the Carlini function, is that there is variation in the templates. So you have to generate a ton of stuff before you find something that's really close to a particular template, because there might be variation in some part of the image. Like the attack is not doing any masking. That's just for the ground truth. And so that, I think you'd really have to design something specific for these templates to push the precision up to higher here. And then we show one more curve here in magenta, which is our hybrid attack run on Stable Diffusion version 2. The reason we didn't do it on Stable Diffusion version 1 is because there essentially is, well, none that we found, no exact copies. So how can we characterize, what factors lead to this copying? What we're going to show here is the position of a copy within the duplicate histogram. So for instance, this bin here at 10 to the 4 is saying 10,000, this is at the 10,000th location within the duplication histogram. And I think this is duplicated several thousand times. And so you can see duplication alone is not explaining why they're copied, right? Because these are falling way later. There's stuff that's duplicated way more than some of these samples. And in the original work, they hypothesized that maybe it's anomalies. Maybe this wacky image of Sylvester it's just so weird that it memorized it by default, but that's actually not the case. Okay. And what we found was, if you look at the multimodal duplication rate, so now we're looking for something that's duplicates in image and text. And for the text, I did something really explicit. I just compared the texts, equal. It's not a feature. It's just exactly the same text. And that's where you can see exact copies have a way higher rate of multimodal duplication than non-verbatim copies. So here, I'm just comparing these copies in blue to these bars in red, which are non-copied samples that have similar duplication rates. So this is maybe one factor leading to the copying is the multimodal deduplication. I'm just going to touch on one more thing here about the template copies. So you can see that they're way less duplicated than exact copies. These bins here have just several hundred duplicates per sample. And so what's going on here? So what we're going to look at here is we're going to take a query of a template and retrieve some stuff and just see what's in the data set. And for templates, you get several hundred exact copies like this one. So I show the first nearest neighbor in this first column. But then you get all the templates within the data set. Okay, so this is where kind of the variation in the generation is coming from, is these very varied images. So you can actually detect these if you use a more relaxed duplicate threshold when you do your dedupe. And I show that in red here. But then you start to pick up a bunch of other stuff for other samples, right? That is clearly not duplicates. So my suspicion is that you could do another attack, potentially find more templates by doing a more sort of relaxed dedupe, And then in this case, this duplicate histogram would look way different, and maybe templates would actually be more duplicated here. And you could also use this maybe to improve training. So there's one work that's SemDedupe, which is showing that you can throw away basically even stuff like this, just throw it away entirely, train clip on this, and get the same performance. So I would like to see what happens, when you train throwing these kinds of duplicates away for DDPM, and does that solve the template problem? So we can't actually retrain Stable Diffusion; it's extremely expensive. But we can study, diffusion models that are already trained, and look for copies there. So what I did is I just took the top prompts from the white box attack again, and then I just plugged them into a bunch of different models. And kind of I'll just focus you in on just these first two rows here. Stable Diffusion version 2 actually deduplicated using a perceptual hash. And you can see that the same exact copies don't appear, so there's only 4, but templates are still appearing, right? So there's kind of still a similar level of template copying in Stable Diffusion version 2, and that kind of ties into this picture here, because they removed these duplicates, these p-hash duplicates. They didn't remove these, right? So that's my suspicion of why this is still happening for Stable Diffusion version 2. And then we show, for instance, Midjourney, it's totally closed source. You can plug in the prompts for templates and it's popping up. And I would more attribute this is more kind of similar to what they call universal transfer in adversarial examples. It's, these prompts that are copied by one model, you can plug them into other models, train, totally different, and they're still being copied. Here's just a couple of failure cases of the ground truth labeling. So this was really, I would peer at the images that were labeled as not copied, and I would see a lot of stuff like this. So all over the place, I saw templates, exact copies, where it's so close. And these generated images here, so we have the real ones on the left and then the generated on the right. And these are not labeled as copied by our ground truth metric just because they fall right below the copying threshold. These look copied, right? Like the fact that it says business here, and the other thing is these really share the same properties of other copies. They're very repetitive. You see this image multiple times. So it's just to say labeling this is very challenging. Because you definitely don't want to be subjective, right? Like you don't want to use like a perceptual metric, because then you get stuff that's way different. So you really have to retain the objective of an extraction attack, which is find something that's exactly the same, that maybe be kind of robust to some distortion. So just as a recap, we found high level of duplication on layout 2 billion. We use the duplication rates to hone in on some captions to run our attack on. We introduce an efficient attack that's sort of exploiting synthesis with a few time steps. We looked at template copies because we could evaluate more stuff. We found some more versions of copying not covered in the original work. And we showed maybe some factors leading to copying, and maybe why templates are still being produced by new models, even those that deduplicate. So what happens if you train on a data set that's using a very relaxed dedupe for a diffusion model? And how do we create a more robust ground truth, that's accommodating a little bit of distortion? Thank you for your time.